Hey y'all, welcome back to MathRescue. I'm Andre and I make content to take away the stress of learning math. In this video, we're going to graph a rational function with an oblique asymptote, so you can see what happens when the end behavior follows a slanted line instead of a horizontal one. Take a deep breath, we're going to slow this down, break it apart step by step, and make it feel super easy. Let's talk about it. Alright, so this is probably one of my most valuable videos. This is going to show you physically where everything lies on a rational function, kind of how everything, all these key features kind of come together. So here's the picture of the function, right? So it's this red curve right here sitting on this grid. And first thing we're going to start by doing is finding the zeros. Zeros is another word for x-intercepts. So we want to find the x-intercepts. Now, any place where the numerator is 0 is going to create a 0 output value. So let me show you what I kind of mean by that. So like, for example, if I say 0 over x plus 2, and let's say x equals 8, it doesn't matter. I'm going to get 10 over 0. I'm sorry, 0 over 10, which if you put it in a calculator, it's just going to be 0. So when we are looking for the zeros, when we're looking for the x-intercepts, all we really care about are the places where the numerator is going to be 0. So let me grab my numerator, x squared plus 4x plus 3. I'm going to go ahead and set it equal to 0, and I'm going to go ahead and solve to see which x values would satisfy this equation. I could go ahead and factor here. Because this is my shortcut factoring, I'll just go straight to the parentheses. So I'm looking for something that's going to add to 4, multiply to 3. That should give me 1 and 3. If this is seeming kind of foreign to you, you can always review your quadratic skills, because that's what we're doing right now. We're just solving this quadratic to see where it would be 0. So I set up ZPP, zero product property. So I get x equals -1. That's going to be my first 0 that I found. And I'm also going to get x equals -3. Now, here's the cool thing about Desmos. We just did the analysis, right? We just did all the algebra for it. You might be sure, you might be unsure. If you are unsure, we can immediately go over and check to see that our picture matches up with what we found. 0, -1, -2, -3, -4, -5. So you can see that in fact we did find the correct x-intercepts, the correct zeros. So let me go ahead and record those. And this is why I like Desmos so much, because it makes everything so physical. It makes it so that you're not just finding and calculating random numbers, you're actually identifying locations on the grid. That's when math really starts to spark up and really light up. So next we want to find our asymptote. So there's kind of two paths that we're going to take here. We want to start off by looking for the vertical asymptote as well as the horizontal asymptote. And this is going to get kind of interesting. We'll put a little star right here. So let's start off with our vertical asymptote. So our vertical asymptote comes from a discontinuity. And the only place where our function is going to have a discontinuity is going to be things that'll make our denominator 0. Because we can't divide by 0. You get undefined. So I'm going to grab my denominator. I'm going to set that equal to 0. Subtract 2 from both sides, right? Because I'm solving this. And I get that x cannot be -2. So that's my discontinuity. Now, this discontinuity, there's two types that you can get. For right now, we'll just go ahead and assume this is our vertical asymptote, x equals -2. The vertical asymptote must be entered in as the equation of a line, and I'll show you why in a second. Let me just label these real quick. This is the domain. We're excluding -2, and this is the vertical asymptote equation. So If we graph that line, if we graph the line x equals -2, that would show up right here. And I want you to observe how the red curve, so our rational function, is getting perpetually close to that green line, but never actually touching it. That's what we call our vertical asymptote. It's something that our function is perpetually approaching. All right, now let's go to the HA. So for the HA, there are 3 cases. And so you look at your notes and you say, okay, which of these 3 cases do I fall under? The 3 cases are determined by the degrees of the numerator versus denominator. So here's a degree of our numerator. I just circled it. The degree of our denominator is an invisible 1. I just kind of circled where it would be if it wasn't invisible. You have a case where the numerator has a greater degree. You have a case where the degrees are even. And then the third and final case where the degree on the denominator is greater. In our case here, when the numerator has a greater degree, we don't have a horizontal asymptote, but we have the possibility of what we call a slant asymptote or an oblique asymptote. So how do we find it? Well, to find it, what we want to do is we want to find the quotient of the division. Don't worry about the remainder. You really just want the linear quotient from dividing the numerator and denominator. So I'll set that up with long division. X squared plus 4x plus 3. That's my dividend. My divisor, x plus 2. I'm going to have to make a little bit of space here. Let's just move this just all the way over here. My OneNote is like lagging a little bit. I think it's because I have all these notes in just a giant OneNote file. Anyways, so let me go ahead and start my long division. Bring this down real quick. Okay, so I'm gonna start with multiplying by x. I take x, I multiply it by the divisor. I get x squared plus 2x. We go ahead and we subtract. Very important, you put the parentheses up or else you might not subtract both terms. So these cancel. I also get 4x minus 2x. That gives me a 2x. I bring my 3 down. And then I want to multiply by 2. So I take the 2. I multiply the divisor by it. And I get 2x plus 4. Let me move that over just a bit. Where do I have space? We'll put it right here. It's tight, but we're going to make it work. All right, so these cancel. And I get 3 minus 4, negative 1. It doesn't matter. That's my remainder. I don't need that. What I really am interested in is my quotient without the remainder. Because that quotient ends up being, we end up thinking of it as a line. So y equals x plus 2. You might recognize that because it's in slope-intercept form. Let me move it up so you can see it. And put it right here. Cool. So that is the equation of the line of our slant asymptote, our oblique asymptote. So we can graph that as well. Let me graph it in this purple color. So quick linear function review, right? We'll do our y-intercept. So our y-intercept is 2. Our slope is rise 1, run 1. And then I'll just go ahead and connect those lines. And you can see how it fits perfectly in this kind of diagonal space that's been left there between the two pieces of the rational function curve. So those are our asymptotes. So we found the zeros, we found the VA, we checked if there was an HA, there wasn't, and so we then found the slant asymptote or oblique asymptote. I do want to just show you the graph drawn out one more time. I just want to really emphasize how useful Desmos is as a tool. So you can see the red curve is our original function. Desmos does a great job of showing that curve on here. Desmos allows you to click on the x-intercepts. Then from there, I did the vertical asymptote in blue. Put it right there for us. And then it also did our slant asymptote right here in green. Sorry for the issues we're running into here. Getting a lot of lag from OneNote. All right. So if you found this video helpful, please like and subscribe to support the channel. I post videos regularly. My goal is to make you feel super confident in math. See you in the next one.